Hi, this is the video for the class that we missed on week 10, our last class, the firewall class for the compositional algorithms, 270C. Before we jump into some discussion and materials that I wanted to suggest, I just hope that everyone is doing well before the finals week. If you have any questions, I posted the submissions for the RNN homework and open also the submission for the final project that is due at the end of the finals week. So I'll try to be brief. Kind of what I would like to know is, or to suggest as a reaction to maybe what I'm going to tell, and some of the topics or ideas that I posted on the announcement, is what you think will be the future of compositional algorithms. So let me kind of share the screen and jump into some of these ideas. Yeah. So again, this is a class, and I posted this actually on Canvas. So I hope everybody got the announcement. The ideas or the points for discussions were really, as I said a minute ago, possible applications of compositional algorithms. And that also involves, even broader question of relations between the human and the machine in a creative setting. I would say currently there are like tasks like continuation in painting, which means like finding and completing a segment. This is really in more of a either improvisation setting or a production setting that the computer can perform tasks which are relatively complicated in terms of, or complex in terms of musical knowledge, but they're well defined. So you have a missing piece or a sketch, and you want a computer to complete the missing part. And you want it to create an accompaniment and so on. Style transfers. So the question is, what would be the other uses? We kind of follow that line that algorithms could be based on abstract or mathematical ideas inspired by nature or physical models. They can be also trained from data. And in that sense, they will kind of capture maybe some conventions of style or things that were human generated. Who is the artist? What is the artistic voice? Can you make it personal? And then also, how would the user interact with such a machine? How it will enhance their experience or involvement in music making. So opening the can, which means, in a sense, make maybe pre-recorded or produced music more open and adaptive to the public. And in that sense, there's this adaptive music, which is a term, technique for basically recombining pre-recorded clips in different ways in video games, is slightly different technique. We didn't address it so much in our class, but you can think about the Mozart dice game as some sort of managing a data set. Okay, in the case of Mozart dice game, it created infinite variations, and you can see that this might be required even in a game setting where you're exploring and you're staying in the same level or same scene, and the music has to keep giving it background. So how you compose a music which is between being random or indeterministic and a well-composed, thought-out form where everything is perfectly timed. It's a control of musical form. How do you make smooth transitions, developments, and the whole narrative. That kind of makes also question or distinction between what's an instrument, what's an agent, right? Instruments, you have total control. Agent has its own autonomy, but now you want to actually communicate with something which is between an instrument and an agent. So in that sense, would it help being productive to those who produce music, or have some kind of creative communication between human and machine in ways that involve you better or deeper in in consuming or experiencing music, and the whole kind of the vision maybe of a musician that creates and a music lover that only kind of consumes what he likes, maybe it blends. So I think technology and algorithms could be interesting here. So let me show some examples maybe of works as one thing to get started with this discussion. Some of the pieces that I've been working on or composing. So this is an example using one of our machine learning algorithms in so-called machine improvisation setting. And this is SOMAX. So it's sort of, in some sense, related to the models we discussed, like n-gram models, Markov models, or you can think about variable memory length models like factor oracle. In this case, it's a slightly different version of a machine that does this query. I mentioned like query into factor oracle. Basically, you have a model that tells you what are the possible combinations of sequences, what are similarities across the piece, okay, and then you can actually input another musical sequence and we'll try to kind of find the best continuations or the best corresponding sequences. So here the query comes from the musician. This is me playing on the keyboard, and the memory that the computer uses for improvisation is Stravinsky's Rite of Spring. So of course I kind of like learned more or less and was familiar with at least specific segments of the piece. So by playing, I would basically kind of improvise or remix that piece. Has a model of kind of decay memory. For every note that I go, basically other points along the piece that kind of match to, note, 2 notes, 3 notes, and so on, start accumulating the memory. There is kind of a decay, a model of the history. But the longer sequences that I produce, the more likely the machine is going to be reminded of that particular motif or segment in the Stravinsky Rite of Spring, and it will basically play segments from that piece. And so let's just kind of hear it for the sake of kind of giving it like musical rendering.
Power your flight with light and strong.
Sorry about all the ads. And I think it will not end in 5 seconds. So let me kind of like see if I talk while it's playing. But I think the idea itself, it wasn't clear which parts of the music actually belong to me or what goes into the machine improvisation, because it's all playing on the piano. But I could tell you that I was just playing few notes, and with these few notes, the machine would generate complete many more textures. Okay, I think that's enough to give the overall idea. I mean, I love Stravinsky, and specifically this piece. It's a very particular style. Those who are familiar with the piece might have recognized, some kind of canonical moments from that piece. So I don't know if you call it opening the can, if you call it really an improvisation, but I think for me, besides the fact that I could perform and actually have sort of an improvised piece that was much richer than what I would play, I felt myself sort of like that, kind of being in the head of Stravinsky in some way, able to recombine elements. So yeah, I don't know even how to explain exactly that musical sense, the musical sense. But I think it was a fun, as the musician, it was a fun practice. In terms of what it means to the audience, I would let you judge that. What else? Maybe another example, which is a different way of composing. This was a pre-composed piece, so everything was notated eventually. And this one was using neural networks. So it's kind of a style transfer. And the idea was to feed, this is Prokofiev, based on Prokofiev. So it was a neural network trained on Prokofiev's sonata. And by training, what it did, it wasn't trained in a sequential manner. It was trained to reproduce segments, so bar by bar, actually half a bar by half a bar. So it was like this. This is what some of these autoencoders or neural networks, we didn't cover this, but you can think about this as little representations of music, which instead of storing a specific segment, it stores in the neural network possible, ways of generating, but pretty short segments. These are like half a bar segments. Okay, so you can bang it with some musical input, and it will kind of try to analyze the musical input and regenerate. But unlike the previous example where the regeneration was done on a long sequence and trying to find sequences in the other music, here every note would actually trigger, or every few bars of input would trigger, every few notes, half a bar of input would trigger another half a bar of output. So how do you perform with this thing? So it basically maps some input to output, but changing in some sense the style, okay? Let's say bar by bar. So what I did, I fed another piece into this network after it was trained. So that was, again, Prokofiev, in fleeting visions. So I call it in deep fleeting visions because you have this neural network, deep learning stuff. And it will basically take an existing piece and re-render this in a different way. Now, why I did that? Because I did want to keep the original design. I wanted that musical form to stay fixed. The initial melody, wherever it repeats and repeats again, in some sense, the network would translate it in a way that is recognizable. So you could actually get the notion of the musical form, because the original Prokofiev in Fleeting Visions pieces are very short musical kind of episodes. And what is lovely about them, they're like little etudes, they're little statements, okay? And I wanted to be able to recreate this whole idea, but very different kind of musical surface. So I think the first piece I'm playing is the original, one of the original Prokofiev pieces, just so you can hear what is the original style, and then I'll jump maybe to some other piece that. So the original Prokofiev sounds like this. So these are like 1 minute little pieces, okay? But you could recognize, I mean, there's a little story going on because it started something and then the same chords come back and then there's this melody going in. And it's like looking at this miniature painting or miniature creation of art, and this is in sound and time. But I think I kind of like follow this whole expression here. So I wanted to keep that feeling or that sense, but with a very different musical rendering. So I'll play the one piece, the first one that I did, because I did a sequence of them every time, feeding another Prokofiev piece into the neural network, and eventually notating and learning myself how to play. Yeah. So, I mean, I don't know if people are familiar with this sort of like neotonal style. It has maybe going a little bit outside of tonality more than even the original Prokofiev. But, these are not Prokofiev's, Prokofiev didn't write this second piece, but it was really based on generating that sequence of musical expressions using a neural network that was trained on these like generative mechanisms on this autoencoder, if you want the technical term, trained on 1 bar or half a bar segments, and triggering this with another music, and eventually playing the music that came out, not the original triggers. They're kind of related in the sense that it was still musical input that generates musical output. Only in this case, you didn't hear the input, you only heard the output, and the network was trained in a very different way. It wouldn't look up exact segments, it would really generate those segments. So kind of a different take on the idea. I think one common line is that you, at least in the way I approach this, because a lot of what I'm doing is kind of related also to improvisation, is that a human is part of the loop, okay? And this is slightly different from the way we approach the composition algorithms, that you provide maybe the initial idea, maybe you train it, but very little control. I think the control here is super important. Let me try to get maybe sometimes going in. So I'll probably just switch to a couple more examples or ideas. Actually, instead of this, I think I showed parts of this video, but I'll jump to some other slides. So what is machine improvisation, or kind of just go back and forth and jump between slides from either some talks I gave or let's see, or maybe some other papers. Okay. Sorry about browsing. So yeah, so kind of an idea of an agent architecture for interaction. Okay, so this is really a topic that I chose to talk about today. And in this agent architecture, basically, we have a listening component, okay, that usually translates the input music to some symbol, okay. it's very hard to think about the audio itself in the generic audio format. You have to categorize it, represent it in some way. On the other hand, you might have a specific memory model, a data set, or some way of generating these things. So the machine learning, in some sense, is kind of there is the phase that listening is needed to create, memory models and learn stuff. But then also it's required during the interaction. So that symbolic part goes to learning. It also goes to the interaction part. And the interaction is, as I said, it could be query in different ways, okay, that operates on an existing model. And then, of course, there's a question of how do you, from the interact or the input signals for the interaction, how do you choose from all the possible reactions or predictions or things that this learning and memory model combine? You can think about them as one machine learning model. You can think about this one being the learning part, and this is kind of stored models. So we're talking a little bit about policies, reinforcement learning, the idea, and of course there can be also another control and external input. You can call it scenarios that guide the choices in a way that is more predictable. Okay, so these are things that we kind of didn't really go into in the class, but you can see that a lot of these algorithms, especially the machine learning ones, are required to enable such a system to work. So again, the scenarios and everything come in. I think I mentioned this variable Markov oracle. There is a Python notebook just explains the factor oracle, which is the core string matching algorithm that we used. Variable Markov oracle, which was also known before as audio oracle, actually uses this algorithm on audio with features, and there's some extra steps to find the best representation of repetitions. So I think we played this specific example in class of Bernard Luba improvising. Now, if we have scenarios, then we actually have a problem of trying to predict something. So if the factor oracle kind of uses the past or even the future, but of the original data set, it doesn't have the future of what's going to be performed. So if it uses the previous playing events to predict the next thing, there might be many different predictions. You can think about some kind of almost like a beam search idea. In the factor oracle, actually what you have is, if you have the past A, B, okay, it might find some continuations, A, B here, and B, A, B here, and A, B here, and another A, B here. So the question is, how would you basically choose what will be the best continuation? This is really in the model of the first piece that I was showing, where the improvisations were done by querying, okay? So in that sense, what you need is, in some sense, kind of a scenario or set of expected labels that will tell you, okay, from all of these possible continuations, you might want to be able to choose only subsets. So in some sense, you need an extra information, maybe the chords, maybe segments, maybe some other agreed possibilities for how the generation is going to develop into the future. So you choose which one to go forward, okay? So in that case, the continuations for this set of events, in this case is C, in this case is A, in this case is, so this one will just generate CA, this one may maybe generate CA and then continue in something else. This, you have the past memory and you have future scenario, okay? And with this future scenario, you can actually have higher weight jumping into events that actually match also something that you planned. So you can think about these being the notes and the scenario being the lead sheet that gives you the chords that label basically longer segments. So it limits your selection and guides it towards specific improvisations. And some examples of improvisations. Actually, this is reference to very different work that now is becoming very exciting, and this is using a representation based on a specific signal processing or analysis tool, you know, a hierarchical transformer that one of our students, Kechen, with other students actually from also some other universities, developed. And I will not go into this model itself, but it can be used for source separation. And in this case, what we did was, and this was an event for commemorating 100 years of his Toots Thielman. He is a harmonica player from Belgium, very famous, and we wanted to kind of create a virtual model, maybe improvise on Toots recordings, a little bit like what I did with Stravinsky, but we didn't have his solos, okay? So what we had to do, first of all, is to use his recordings with other musicians with piano and other ensembles and extract his model. Then we would build a model, and then we would basically improvise on that recording, where the segments will be basically taken from his own voice and his own ways of expressing and building melodic structures and so on. So let me show an example. This is one of the collaborators of this work, who is professor in France, and he chooses to present himself as DJazz, Maximilien, and he's actually improvising in the style of Toots. So here's a short example. So again, it's a different type of use of very much related technology. And you can see that what he was doing on the pad, on the controller, was he wouldn't query with specific musical input, but the harmonica sound that you heard was improvised based on segments of recordings of Toot. So it was not really continuous recording. It was very much done in this sort of a query audio method. And he would basically influence some of the choices. And you could see that sometimes Toots would kind of like loop itself and have faster passages, sometimes slower ones. So more of an expressive control of rendering a piece. And you can basically perform the same piece over and over again with the same accompaniment. And slightly have variations on the way the harmonica, the virtual, this avatar works. So let me kind of summarize some of these ideas. Kind of the paradigm is we need some representation of audio. Since I'm using here some terminology from neural networks, you have some latent encoding. Now this latent encoding only captures part of the representation of music. In that sense, it's lossy representation or partial representation. Same thing as you say, a chord is a partial representation of what's happening in music, because in music you have multiple voices and textures and voice leading and so on. So this lossy representation needs to be really quantized or put into categories, and these categories might be different, not only across different musical styles, but even across specific musicians. And then using this, we might want to be able to, so we build this sort of a generative model that goes between the actual data and this latent representation. And this generative model goes back and forth. You can generate more data. You can learn the causes or the hidden representations. And we're also talking about some strategy of long-term policy, maybe, or interaction between human and a machine. So here, kind of like long-term rewards and ideas for actual machine learning research. So given this kind of an idea, I would say the cognitive motivation is what we call deep music information dynamics model. So again, you have the music itself, and you have some representation in the brain. And this is the mapping maybe of short segments. You know, if you want to think about the half bar of Prokofiev, and that captures, you know, a representation. And then you have a sequence of these representations as they go over time. And you want to basically have both ability to predict in a lossy way the continuation of music, and maybe predict the next chord, maybe the next phrase, maybe, you know, you anticipate, you know, when the chorus ends and the verse begins, or so on. And so in that sense, the same ideas of lossy representation, prediction in time exist here. And, you know, these are kind of more technical terms that we use. This is kind of the encoding, decoding, really the same idea, you know, that was used in that Prokofiev example, learning and mapping the input. In Prokofiev, it was actually generating the output. Here, we actually think about this as some kind of imaginary music that goes, partial music goes in the human brain. And then you can have also a time-based model, which in this case is represented more like that factual oracle idea. But in the main message here, you have predictions in time, you have mapping of instantaneous musical experiences, which are lossy and partial. And the whole idea of this model is that we kind of create, sorry, I'll just do a concept that I just would like to throw in this term. I know that we didn't cover this, and it might sound very abstract, but so-called information bottleneck. So what is information bottleneck? So the idea is that, you know, if you think about, you know, your music X right now and the music Y that will happen later on in time, okay? And then you think about some kind of internal imaginary latent, if you want, representation of that feature C, and then the next set of features in the next moment in time T. The question is, how do we find this latent representation? So what the idea is that we actually want to have something that, on one hand, best compresses, that represents X in the most compact way, okay? And on the other hand, this compact representation should be best predictive of what will happen next. And this is really what is expressed here, okay? So this is, okay, because it's max, so it's min, okay? This is with the minus, if you want to go mathematical here. This expresses the best compression, the minimal, okay, information, or the most negative, well, the information is positive, but this comes with a negative sign. So you actually want this to be smallest representation here, okay? The IXZ should be minimal, and the IZY should be maximal. So most information will go from compressed representation to the future, but with least amount of bits and effort that goes into encoding of C, okay? And in some sense, this kind of a conceptual model of information bottleneck in time, this is why it's predictive information bottleneck. This is kind of the overall framework that guides us in trying to build some of these models. You can think about this as a cognitive motivation. You can think about this just as a technical, musical way that deals separately with, you know, representation, instantaneous representation, and prediction aspects. But I think the idea itself is pretty intuitive. You actually want a very compact representation here, something that is really, you get the essences of every moment of music in a way that is not too lossy. So you can kind of recreate, have good relations, but this is really the smallest choice the best summary of what you see in music, you do this reduction, but that reduction should be predictive, okay? So it should be able to predict basically the next musical element in the best way. And these are kind of competing criteria. So this is kind of that idea of the deep music information dynamics, if you want, that brings this predictive information bottleneck as a framework for building models. I will not elaborate on this too much, except for, one thing that we try to use this is really to explore relations between multiple voices. This is another demonstration of this principle that you need some kind of a lossy representation that allows you to find relations between voices. Okay, so basically, kind of formalize in mathematical terms the idea that good counterpoint, good relations between two voices is that if each voice is basically has a good continuation, so its information rate in that voice is high, okay? So we actually want to have two voices that are kind of meaningful, but also that, they have a lot of relations between the voices, okay? So there is this kind of specific example or specific motivations that we call transfer entropy, kind of ideas from finding causal relations between two sequences. People do this in economics with grandeur causality or stuff like that. So I think the idea of creating communication between voices, or if you want to think about one voice as being a human, another voice being the machine, is one way of saying, well, here's how we want to build nice interaction between music and the machine. If the previous one was just a modeling paradigm, and thinking that good model should be compressive and predictive, here now we talk about relations between two models, okay, and we find out that the communication between two voices should be done in ways that are partial. So what we did was an experiment here, and this is what I'm kind of summarizing here, is trying to find all kinds of partial representations or lossy representations. This is R, which is the rate of encoding. The smaller encoding means more compact representation. And the idea was that we're trying to look for most information that goes between the voices while we compromise on the quality of representation of each voice. And so this is like from first to second to first. And what we can see is that, we get higher values, okay? The higher is the better relation between the voices, and not at very low rates and not at very high rates, okay? Basically, you can see that between the voices, okay, you get good relation between first and second voices at the rate of around 100. Here, high rates is slightly better for the relation of second voice and first voice. But then as we go and either decrease or increase the representation, we lose some information. So it might be a little kind of counterintuitive, but actually, I think it does make sense, because if you look to explain every note in every between the voices, or every relation between every note of a musician and computer, you will not be able to find any relations. But if you're able kind of to abstract the ideas and find the communication on kind of a reduced, blurry way, if you want, that's where things start suddenly working together. So this is kind of done mathematically without really knowing what exactly that reduction is. I can tell you that, with some experiments that we did, we noticed that when you reduce the rate, it still keeps some harmonic structure, but it loses the temporal structure very quickly. But maybe this is the type of information that the reduction allows now to find more relations between the voices and more mutual information. So these are kind of the ideas that we're playing around. Yeah, I will not go into the computational examples, but this is one idea of using these algorithms, which might be very mathematical, but I think they do have a mapping or meaning. And when you think about music, how voices are developing over time, and how I think now we're more and more looking into relation between voices. I had some other ideas in mind, maybe trigger some thoughts. Yeah, and just maybe give some hype to recent work, which is it's still under let's say review, but I can show the examples. So, for instance, this is text and music, very much like the diffusion music, language diffusion model, work by Ke and others. So we give a text description, and it generates music. Okay, and these are some competition. So just to give you some kind of an example of, I don't know, Q Toy Factory theme. Okay. So this is the prompt. Okay, you give it the prompt. It's like diffusion in visual sense, right? Yeah, you give a prompt and it paints an image. So this is all generated by the machine. Here are some other alternatives. Refusion, which I think the quality is problematic, but it was mostly trained on drums, so it's unfair. Okay, I think that's a Mewbird, which is, I think they're trying to commercialize this. As far as I know, they didn't really, at least I'm not aware of them publishing exactly what they do. I think they do this more like the Mozart game or the adaptive music. They have a lot of clips that they know how they will recombine, and they do this mapping from text to clips. So I'm not sure if they actually generated neural networks or they recombine clips, but this is what their sound, Mewbird, sounds like. Okay, so in this case, they actually didn't do a good job. ODLDM, which is, okay, this is kind of a different work. It was trained on a different data set, so it doesn't have as much musical training. So I don't know, I mean, if you think I chose this example because we're the best here, we can take a look into any other examples, maybe, I don't know, hip hop. So this is fashionable lo-fi hip hop. This is the prompt. This is I think that's the refusion second, right? Yes, so lo-fi hip hop. This is what refusion gives. Refusion, I must say, almost always sounds the same. And the Mewbird, okay. So I think it's decent quality. You can argue which one is better as a fashionable lo-fi hip hop. I think ours is a little bit more hip hop like. Maybe it's more rock. I don't know. Classical examples. Well, film music orchestra. Mewbird. Which musical artificial brain interpreted better? I'll let you judge. I think it's pretty amazing to know that you train a neural network with these representations, same representation that we used with the toots. The Marc Chemelier had this kind of strange, whatever we used, put on the head, that sieve. It uses the same representation, trained on a huge amount of data, and also linking this to text using so-called CLAP, contrastive language audio pre-training. Yeah, piano, they're a little bit more difficult examples, but fantastic piece of music. Yeah. Mewbird. Actually, there are a lot of instruments which are not piano. Again, refusion always sounds the same. Sorry, almost seems like I'm doing fun refusion. General live acoustic guitar. Mewbird. I think Mewbird kind of takes more liberties in terms of recombining clips, and it very often uses beats to complement this. Yeah, just go ahead, go to music, LDM, music language diffusion model .github.io, play around with examples. And I promise this to be short, but I cannot get carried away. So just as a short example of applications which could be like musical adaptive music, right? So this is kind of more just to show you in the context of possible architecture for a game client, okay, which actually has some generative music server. Then the question is, how do you translate, the game client to the music? You need some sort of a model. So at least in this article, the proposal was to use arousal, valence, or emotions that will map to the behavior of the users and maybe some emotional characteristic of a scene. But people actually are trying to use more and more techniques that use generative music for games. So what would be kind of examples of what's the difference between adaptive and generative music? So I don't know why I'm showing this as 2 pages, but I think the idea is that in recombination, you have multiple clips that you can choose from, you can mix them together, you can resequence them, so use musical segments, or you can have a generative thing that actually creates the music in runtime. And the basic 2 techniques in adaptive music are horizontal resequencing and vertical remixing, while in generative music, they might have many more possibilities and examples. So kind of giving an example for some sort of a, okay, sorry, I'm just gonna, same person from the previous, Alvaro, just finished his defending his doctorate actually in the music department. And I mean, just looking for some schemata. He developed his own generative music system for games, and I think some of these graphs, they look like patents, and I think he's actually trying to commercialize the system. Why it's so slow? Yeah, so it gives you basically kind of an overall architecture for agents that are needed to generate or have an adaptive music, okay? So tempo and clock is very important, okay, because you have kind of synchronized things. Then you might have an agent for melody, an agent for harmony, something that relates to percussion. He has a separate percussion agent, and all of this is basically combined into a playback machine. So this is kind of an overall scheme for, for the system that you develop. And I think one interesting aspect of thinking about how different modalities or how different musical things need to operate together. Okay, I don't think there's a sense of going into all of these graphs. I was really just wanted to show, this kind of overall a presence of multiple features that need to be combined. In this case, he actually programmed his own sensors, his own style of doing this. And let me see if I have his. Actually, I had in mind to show one aspect of. So this is just an example of. Where's that sketch? Yeah, this is how his interface looks like. Okay, and you can see that you have these different agents. Okay. There's a rhythmic agent, not everything can see, and something that's responsible for tempo. You have harmony agent, you have melodic line, shape of melody here, you have harmony here, and they're all modeled by different generative algorithms. So this is not machine learning. This is actually going back to the things that we're covering in class, algorithms that might be choosing from harmony. They might be choosing some harmonic sequences. They would be rendered into music with different shapes. You would control the density by choosing subsets of notes. So we have seen this idea of chord melody relations in some of the genetic algorithms. We mentioned that. So here you would have a list of possible choices of melody that if you wanted more, I don't know, more emotionally engaged music, will get more notes which are maybe outside of the scale or increase the harmonic vocabulary. And you have these different pre-trained models, and you would basically integrate, you would, in the generative sense, you would interpolate between different presets of these different agents, and that would be mapped to the musical scenes through this kind of a, so it's all being rendered in Unreal Engine. So you can see the game, and you can see how actions in the game according to the scenes move these parameters, and that's how things are being generated. So this is really an example of implementing, going back, as I said, to generative algorithms. But again, they have multiple agents, they have multiple modalities, and you need these kind of different behavioral patterns that then create sort of a mapping to the user, and maybe some policy of how they would vary according to evolution time. What is the default behavior? Because even if nothing happens in the user, you don't want to keep being in the same musical sense all the time. So I think that kind of summarizes the ideas or examples that I wanted to show. I'll go back to our, so I think this is pretty much, and the last word I didn't cover at all, and if somebody's interested in the slides, of course I skipped, or I had a lot of things that were still in the slides but we didn't cover. Part of them were advanced materials that I didn't mean to cover so much, or maybe were not appropriate for the class. I think one thing that I did not go into it all is so-called the complex system theory. As if anybody is interested, that might be a good way to relate this back to dynamical systems. Chaos theory, how things build into statistics of like 1/f, and why natural languages exhibit these behaviors. But I think I already took too much time, and it kind of throws us a little bit away from that summary and the questions I posted on the topic here. So I just wanted to point out this example. It links to some videos which are also fun to watch. So it's relatively short, really talking about statistics of languages and how it relates to things like dynamical systems, or even models of distributions of wealth, and this kind of 1/f statistics, and in text it's known as Zipf's law. These behaviors are studied using very different kind of concepts of complex systems. What is interesting also, it kind of relates to also communication between, at least in language, there is a communication model that could be shown that, in certain conditions, communications between two agents result in a language that behaves this way. So maybe that relations, at least for me, it's kind of an interesting idea to see what kind of languages can be developed, and what kind of musical interaction can be developed that are actually most informative, or best communication between either musicians and audience, and maybe they have to obey specific statistics. Okay, so thank you everyone for taking the class, and again, good luck with your finals, and I'm looking forward to hear more ideas from you and your homework and the final report. Okay, all the best.